Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am starting module 10, and in this module I want to discuss the membrane analysis of pressure vessels and tank. Now, so far I have discussed the theory of membrane analysis, that how a momentless state in a thin shell is developed, and this is useful for analyzing the stresses under the external load, and the results produced by the membrane analysis are reasonably accurate except at the boundaries. So, that things I have shown with several examples of spherical domes, conical shells, and then domes with opening, and therefore, today I want to extend this membrane analysis to a kind of structure which is also a thin shell of revolution. With the help of membrane theory, I want to find out the state of stresses in the pressure vessels. Okay. So, our topic will be membrane theory of pressure vessels. Now, first let us discuss what is pressure vessel. Pressure vessel is a container which is used to store gases or liquids at high pressure. Generally, the pressure in the vessel is more than the atmospheric pressure. So, the container wall, the shell has to be designed properly, so that it can resist the higher internal pressure. Now, you can see that pressure vessels are mainly made of metal structure, and especially the mild steel is used to fabricate the pressure vessel. Pressure vessels are generally of cylindrical type, and it has head at the both end, which may be a part of a sphere, that is spherical part, or it may be a ellipsoidal part, or it may be any other form. So, mainly the ellipsoidal and spherical part is common at the closer end closer. So, pressure vessels are closed shell actually, and predominant load is internal pressure. Self weight is negligible compared to the internal pressure. These are structures to be grouped as shell of surface of revolution. So, this type of pressure vessel is formed when a curve is rotated about an axis of revolution. So, here axis of revolution is horizontal, and here a straight line is rotated to form a cylindrical portion of the pressure vessel. Similarly, here this say here it is a spherical part, the head that you are seeing at the end is spherical part. So, arc of a circle is rotated about the axis of rotation to form the closure of the shell, end closure. Okay. Pressure vessels are is demand in the industry for carrying this LPG, or you can say the oxygen cylinder, or petroleum liquid or gaseous substance are stored in the pressure vessel and carried to the site for different use. Now, different form of pressure vessels are found. One is circular cylindrical vessel, then circular conical vessel, spherical vessel, vessel in the form of ellipsoid of revolution, vessel in the form of circular torus. So, you can find the different types of geometrical shapes are given in the pressure vessel. So, one by one we will discuss and we will see how the theory is developed. Theory is our membrane analysis for axisymmetrical loading condition, and our target is to find the meridional stress n phi and circumferential stress n theta for the design purpose. Okay. Now, since in the axisymmetric condition the analysis is carried out, so we assume that the membrane shearing force n theta phi and n phi theta is 0, and deformation and loading whatever is produced in the shell or acted on the shell due to internal pressure are all independent of theta. So, thus following two equations are to be considered only for the analysis. So, one is a differential equation that you are seeing d by d phi r into n phi minus r 1 n theta cos phi plus r r 1 w phi equal to 0. Now, here this the n theta is the circumferential stress and n phi is the meridional stress. R 1 is the principal radius of curvature of the meridional curve and r is the radius of the parallel of latitude. Okay. So, these are the symbols, and it is a differential equation of first order, but you can see in the first equation the variable n phi and n theta, the unknown variable n phi and n theta are involved. And in the second equation you can note that it is an algebraic equation given by n phi by r 1 plus n theta by r 2 equal to w r, where w phi and w r are the component of the load in the meridional direction and radial direction respectively. W phi is the component of the load in the meridional direction and W r is the component of the load in the radial direction. Radial direction I mean that is a direction along the normal to the tangent at the point of meridian. Okay. So, solution of these two equation will give you the n phi and n theta. Now, from the second equation here we can express n theta in terms of n phi, and then we can substitute back in the first equation. So, that the first differential equation is converted into a differential equation of single unknown variable n phi. Okay. So, then n phi can be found out by integration of the differential equation. So, n phi is given by 1 by r 2 sin square phi, and integration is carried out from the limit, say one limit is phi naught lower limit and upper limit is some other phi. The phi is measured from the axis of rotation. R 1 R 2 are the principal radii of curvature and W r is the radial component of the load. W r cos phi minus W phi sin phi into sin phi d phi. So, right hand side and left hand side is n phi and right hand side contains this integral expression. Now, because we are carrying out a definite integral, so constant of integration is not written here. Now, if I multiply this equation by 2 pi r 2, 2 pi both the sides and being this r 2 here, then we get this term, the left hand term is 2 pi r 2 sin square phi n phi and right hand term becomes the integral expression whatever you are getting. Only the multiplication is done with by 2 pi. So, therefore, 2 pi term is coming here. Okay. So, this expression can be interpreted physically. So, physical interpretation is that if we see the left hand side, n phi sin phi will be the, say here it is a part of the shell, the surface of revolution, and n phi is the meridional stress that is acting along the tangent at the meridian. So, n phi sin phi is the vertical component of the meridional force at a angle phi. Now, when n phi sin phi, this is the force per unit length, and when it is multiplied by the circumference at this parallel of latitude, then it becomes the total vertical component of n phi. So, left hand side of this equation represents the total vertical component of n phi. So, 2 pi r 2 sin square phi n phi is the total vertical component of n phi. Now, if I see this term, this W r cos phi is the component of the load along the radial direction, and W phi sin phi is the component of the load in the meridional direction. So, this sum represents the total vertical load. So, total vertical load multiplied by the surface area. What is surface area? If I take a strip here, r 1 d phi is the width of the strip, if the differential angle is d phi, and the circumference is 2 pi r, 2 pi r is the circumference. Okay. Now, r can be related with r 2, that is r we can write as r equal to r 2 sin phi. So, therefore, you are seeing that here r 2 sin phi term is there, r 1 d phi term is there, and 2 pi term is there. So, the surface area is inside this integral term, elemental surface area, and the term inside the bracket represents the net vertical load, because W r is the radial component of the load and W phi is the component of the load along the meridional direction. So, when it is resolved along the vertical direction and then added, it represents the net vertical load. So, right hand side represents the net vertical load acting above the level phi. So, this equation represents a force balance along the vertical direction. So, with the help of this meaning, that physical meaning, that total component, vertical component of n phi at any level phi should be balanced by the total vertical load above that level, we can find out the unknown stress component phi, n phi. Now, once n phi is found, then n theta can be calculated from this algebraic equation. Okay. Now, let us go one by one different types of pressure vessels. Okay. First, let us take the circular cylindrical vessel. Okay. Now, here circular cylinder of radius r is considered and it is acted upon by internal pressure P. Okay. The cylinder is provided with a enclosure, and enclosure is in the form of a flat plate. Okay. But in practical purpose, the enclosure may not be a flat plate, it may be also a shell, a spherical shell or a ellipsoid or any other form. So, here for the simplicity we have taken the enclosure as the flat plate, because our intention is to find out the membrane stresses in the cylinder. Okay. So, we will use the two equations. One is this equation, that is algebraic equation n phi by r 1 plus n theta by r 2 equal to P. Now, here the W r, the radial load is P and it is positive, because the positive direction of W r is this away from the center of, away from the axis of revolution. So, here the positive convention is taken and therefore, this the W r component, W r is here simply is the radial pressure P. that is actually internal pressure in the pressure vessel. Okay. Now, this type of shells of revolution have one curve as a straight line, because when a straight line is revolved around the axis of rotation, then a circular cylinder is formed. So, the radius of curvature of the straight line is infinity. So, therefore, this first equation, the n phi by infinity. So, this goes to 0. So, only this term remains, n theta by r 2 equal to p. Now, here for the cylinder, r 1 equal to r 2 equal to r. So, radius of the circular cylinder. So, therefore, n theta is readily obtained as p into r. So, the value of circumferential stress n theta, which is called the hoop stress, in this case hoop stress acting along the circumference, is p into r. Now, let us find out this other component of the stress, that is n phi. We are calling n phi, that is along the direction of the meridian. Here meridian is a straight line. So, sometimes in case of analysis of cylindrical shell, the notation n phi can be replaced by the n x. Sometimes in some book or some author prefers to write the circumference meridional stress in the cylindrical wall as n x instead of n phi, because n phi is related to sphere, but anyway we will keep this notation consistent. Here n phi is understood as a membrane stress which is acting along the meridian. Even meridian is a straight line, this will be denoted by n phi, but somebody can replace it by another term n x. So, many author prefers to replace this n phi in case of cylindrical shell with the notation n x. Okay. So, for finding the value of n phi, consider the free body diagram at the end of the shell. So, if I consider the free body diagram at the end of the shell, say for example, this top plate, if I consider the top plate is acted upon by the pressure, internal pressure P, this is the only load, and the self weight is neglected. So, it has to be balanced by the vertical component of n phi. Okay. Now, n phi is acting along the circumference of the plate. Now, plate is a circular. So, the total n phi acting at this level is 2 pi r n phi, where r is the radius of the circular cylinder, and it should be balanced by the external the internal pressure that is acting on the plate, circular plate, which is of radius r. Total load due to internal pressure, upward load, here you can see acting on this plate is p pi r square. So, therefore, n phi is calculated as p r by 2. So, this is generally referred as the hoop and longitudinal stresses respectively. So, hoop stress we can find out this n phi hoop force is the n theta, there is the circumferential force. If I divide it by h, if I divide n theta by h, I will get the hoop stress. So, hoop stress is p r by h, and the longitudinal stress, that is the meridional stress, I call it in general sense, will be sigma phi equal to p r by 2 h. Okay. So, this is the analysis of circular cylindrical pressure vessel. Okay. Let us take a circular conical vessel, circular cone of dimension of slanting slide L. So, you can see this is the circular cone and it is closed at the end. Okay. It is formed by generating a slanting straight line, inclined straight line about the axis of rotation, and then we form a cone. However, the closure is provided with a flat plate. Okay. So, the alpha is the angle that the slanting slide makes with the horizontal. L is the length of the slanting side, and then other parameters are, say, we will find it out from the geometry. Take a level, say at this level we want to calculate. So, this plane is at a distance of s from the apex of the cone here. So, at this position we can relate this, the radius of this circle, parallel circle, with the inclined length, and also we can relate this second principal curvature R 2 with this inclined length. One thing can be noted, that this type of shell has 0 Gaussian curvature, because the one curve is straight line. So, for straight line the radius of curvature is infinity. So, therefore, the curvature is 0. So, product of two principal curvature is known as Gaussian curvature, and hence the Gaussian curvature for this conical shell as well as cylindrical shell is 0. Now, if I make use of this triangle to write this relation S cos alpha, S cos alpha is your this side. Okay. S cos alpha by R 2 will be cos 90 degree minus alpha. So, that relation is used to find R 2, the second principal radius of curvature, in terms of the inclined distance and the semi apex angle. So, it becomes S cot alpha. Here of course, this alpha is the angle that we have denoted as the angle made by the inclined side with the horizontal axis. So, semi apex angle will be alpha by 2. So, however, this relation is coming out in terms of full angle alpha. So, R 2, the second principal radius of curvature, is equal to S cot alpha. Now, we make use of this relation n phi by R 1 plus n theta by R 2 equal to p. But you can note here, you have already noted that one of the principal curvature is infinity, that is R 1 is infinity, the meridional curve is here straight line. So, therefore, n phi by infinity plus n theta by R 2 equal to p. P is the internal pressure, and this term goes to 0. So, therefore, this circumferential stress, or you can call it hoop stress, is equal to n theta into p into R 2, and R 2 is S cot alpha. So, we can get the circumferential stress as n theta p S cot alpha. Okay. Now, we want to find the meridional stress. Meridional stress can be found by integral expression, or using the physical meaning of the integral expression, we can find the value of the meridional stress n phi. Now, here we will use the physical meaning of the integral expression instead of carrying out the full integration. So, to find n phi, consider the free body diagram at the end plate. So, here you can see the end plate is subjected to this loading, which is produced due to internal pressure, uniform internal pressure, and this plate is again a circular plate. So, therefore, the total load here will be the uniform pressure intensity P multiplied by the area of the circle. Now, here you can see for the end plate, which is of circular shape, the radius will be S L cos alpha. So, therefore, the total load on this end plate will be P is the intensity of the load, area of the circle is pi L cos alpha whole square. Okay. So, this is the total load. This total load has to be balanced by the total vertical component of n phi at this level. So, if I see the n phi, which is acting along the inclined side, that is along the meridian, and you can see the vertical component of n phi here is n phi sin alpha, and the circumference here is again the circumference of this n plate. So, we write here n phi sin alpha is the vertical component of this meridional stress n phi multiplied by the circumference of the circular plate 2 pi L cos alpha equal to total load at this level. So, total load at this level is produced due to uniform internal pressure acting on the plate. So, it is P pi L cos alpha whole square. Now, you can see here this is balanced. Now, the total internal force that is acting due to the pressure, uniform pressure is downward. So, to balance this load, the n phi should be acting upward. Okay. So, value of n phi is now after simplification is coming as P L cot alpha by 2. So, in this way, in a circular conical vessel, we can find the n theta and n phi. Okay. Let us come to the spherical vessel, which is very common, and due to spherical symmetry, the designer preferred this because analysis is very simple. And even in this some vessel, pressure vessel, the enclosure is made in the form of a spherical is provided with a spherical part, spherical component. So, therefore, this analysis of spherical vessel is also important. So, let us make use of the integral expression to find the value of n phi. Now, here instead of this force balance, that is physical making use of the physical interpretation of this integral, we can find it, but instead of this we now doing the integration. So, let us see how we can arrive at the result. N phi equal to 1 by r 2 sin square phi integration r 1 r 2 p r cos phi minus p phi sin phi into sin phi d phi plus k. K is a constant of integration because this is a indefinite integral. Okay. Now, P r is the component of the load in the radial direction. Now, here load is your uniform internal pressure P, and P phi is the load that is acting along the meridional direction. Now, for the spherical vessel, the principal radius of curvature r 1 equal to r 2 and it is equal to the radius of the sphere r. The radius of the sphere here in this problem is taken as r. P r, that is the radial pressure acting on the wall in internal pressure, is your P, that is we have taken P as the internal pressure, and P phi, that is the pressure along the meridional direction, is 0. So, that quantity we know. So, this integral now becomes n phi equal to 1 by r sin square phi integration r square p cos phi sin phi d phi plus k. Now, for n phi to be finite at poles, k must be 0, because at poles when you integrate it, you will find that only it is the finite value is possible only if you put k is equal to 0. So, therefore, the n phi is found out omitting this constant. N phi after integration becomes 1 by r sin square phi into r square p sin square phi by 2 plus k. So, k is taken as 0. So, therefore, the final result for n phi is p r by 2. Okay. To find the value of n theta, we make use of the equation n phi by r 1 plus n theta by r 2 equal to p. Now, since r 1 equal to r 2 equal to r, we get n theta equal to p r. So, p r minus p r by 2, and again n theta is coming as p r by 2. Now, in this problem for a spherical pressure vessel, both the stresses n phi and n theta are equal p r by 2, and this is expected because of spherical symmetry. Now, let us come to the ellipsoidal vessel under internal pressure. Ellipsoidal shaped heads are commonly used for the enclosure of cylindrical shells, in many cases for steam boilers, reactor and other storage vessels. So, analysis of ellipsoidal vessel is slightly complicated because of the difficulty in finding the expression for the principal radii of curvature. You have to do a lengthy differentiation to find the this principal radii of curvature. Now, let us see how it can be done. We have taken a elliptical vessel acted upon by internal pressure P, uniform internal pressure P. With reference to the figure shown here, the equation of the ellipse can be written as x square by s square plus y square by b square equal to 1, where this origin is here and your x axis, positive x axis is along this direction, positive y axis is along the upward direction, and A is the semi major axis and B is semi minor axis. So, A by B ratio is the very important factor here, you will find it later, which influences the nature of the stress. Okay. Now, here in this figure we see that at any point the meridional angle is phi and principal radius of curvature for the meridional curve, which is ellipse, is r 1 and r 2 is second principal curvature at this point. Okay. Now, the other parameters are at this point the coordinate is x, the coordinate of this point is x y, whereas x has to be measured negative at this point, and this is taken as positive. This is the positive direction of the x axis, but however, since this is symmetrical about this y axis, the analysis of the elliptical part taking a point here or towards the first quadrant will be same. Okay. Now, L is the length denoted here from the point O1 to the crown of the shell. Now, this type of shell, that is the ellipsoid of revolution, has application in steam boilers and reactor or other storage vessel, mainly in industry, and there are some technical name for different regions. This part, this apex point is known as crown, and this is known as, this level is known as equator, and in between this is known as knuckle region. So, there are names given in the three regions, this is crown, this is equator and knuckle region. Okay. Now, let us go to the mathematics part. With reference to the figure shown here, the equation of the ellipse is x square by s square plus y square by b square equal to 1. Okay. Now, this equation can be written as b square x square plus s square y square equal to s square b square. Then y is found as plus minus b by a root over s square minus x square. We want to find the principal radius of curvature of the elliptical curve. So, therefore, we need the derivative, first order derivative and second order derivative. Differentiating it once, we get this expression. First we differentiate this. So, it will be half 1 by root over s square minus x square and minus term will come. So, and then differentiating inside this minus 2 x, this term will come. So, 2 will get cancelled. So, ultimately we will get dy by dx as minus b x divided by a into root over s square minus x square, and you can see here again y is given by b by a root over a square minus b square. So, we can write this in terms of y. So, dy by dx is equal to minus b square x divided by a square y. Okay. Now, taking second derivative of this expression, we can now find that second derivative is minus b square by a square, and this x by y derivative we have to take, because both are functions of x. So, we differentiate, we take the derivative with the rule that we know the differentiation of the expression, say expression which is a ratio of two functions of x. So, first we differentiate this numerator and then it is multiplied by the denominator. So, differentiation of numerator is 1 multiplied by denominator is y. So, first term is y, then minus the numerator into differentiation of the denominator. So, differentiation of the denominator dy by dx. So, it is over. So, numerator of the derivative is complete. Denominator will be this denominator square. So, y square. So, we got this quantity. Now, after several simplification, that is bringing this term, this y that we got it here, and dy by dx also we got earlier, and y square we can now square it. So, all these terms are now substituted in this expression, and then after simplification we finally get d square y divided by dx square equal to minus b a divided by root over a square minus x square to the power 3. That means, we can write also this like that, minus b a divided by a square minus x square raised to the power 3 by 2. So, this is again using the first expression, that y is equal to b by a root over a square minus x square. We can write it in a compact form as minus b to the power 4 divided by a square into y cube. Okay. So, this term second derivative and first derivative is needed to compute the radius of curvature, principal radius of curvature. So, principal radius of curvature R 1, I am taking the absolute value, is given by 1 plus dy by dx whole square raised to the power 3 by 2 divided by d square y dx square. So, after substituting the values that we have obtained here for this second derivative and first derivative in the earlier expression, and after simplification with care, you have to take care, so that no term is missed and the power is appropriately given. So, we find R 1 equal to a to the power 4 y square plus b to the power 4 x square raised to the power 3 by 2 divided by a to the power 4 b to the power 4. So, this is first principle of principal radius of curvature, that is the radius of curvature of the ellipse, actually you can call at any point x y. Okay. Now, from figure here we can see that the tan phi is nothing but dy dx and it is equal to x by L. So, tan phi dy by dx and dy by dx we earlier obtained. So, we write it minus b x divided by a root over a square minus x square, and this is after simplification we can write it in terms of y. Now, the second principal curvature, that is R 2, that line you are seeing here, from this triangle using the Pythagoras theorem we can find R 2 square equal to x square plus L square. So, we can find R 2 as root over x square plus x by tan phi square. So, substituting the value of tan phi here, and after simplification we obtain the value of R 2 as a to the power 4 s square plus b to the power 4 x square raised to the power half divided by b square. So, we obtain two principal radii of curvature. So, R 1 is one principal radius of curvature and R 2 is also one principal radius of curvature. R 1 is expressed in terms of R 2. Okay. So, let us now see the membrane stresses. Let P be the internal pressure in the vessel, then for any parallel circle of radius R naught, say here R naught is x here. So, at any parallel circle, if this is the direction of n phi, then the resolving the forces, the n phi along the vertical direction and equating this to the total load, total force produced due to internal pressure above that level, we can find out the value of n phi. So, that principle used here, and for a parallel circle of radius r naught is here x, we can find that n phi into sin phi, that is the vertical component, multiplied by say 2 pi r naught, that is the your 2 pi r naught will be your circumference of the parallel circle at that level. So, n phi sin phi into 2 pi r naught will be the total vertical component of n phi, and it is equated to the total force produced by the internal pressure at this level. So, it is p pi r naught square. So, after simplification we get n phi equal to p r naught divided by 2 sin phi, and substituting r naught as r 2 sin phi, because r naught you can see in this figure, this is r naught, x is r naught. So, r naught and r 2 can be related. So, r naught is nothing but r 2 sin phi. So, substituting this, we now get p r 2 sin phi divided by 2 sin phi equal to p r 2 by 2. In the figure, r naught is written as x, but here it is denoted at this level, the radius of this circle is r naught, which is equal to x. Okay. Now, take the following equation and substitute n phi here. So, after substituting, we can get n theta as this, r 2 p minus r 2 by r 1 into n phi. So, n theta is now found in the simplified form, p into r 2 minus r 2 square by 2 r 1. So, two values of membrane stresses are obtained, one is n phi, another is n theta. Let us see how these forces are varying along the meridional angle phi. Okay. So, we have got these two expressions, and we also know the two radii of curvature r 1 and r 2. Now, at the top of the shell, that is the crown, r 1 equal to r 2, and therefore, you can see that r 1 and r 2 at the top of the shell, that is your x 0 y is equal to b. You can get here the r 1 r 2 equal to s square by b. So, n phi equal to n theta at the top of the shell, and it is equal to p s square by 2 b. Top of the shell is the pole of the shell, and here the two membrane stresses are equal, and magnitude is p s square by 2 b, where a is the length of the semi major axis. At the equator, you can see here equator is this. So, at this point your this x is a and y is b, y is 0. So, y is 0 here and x coordinate is a. So, substituting this in the expression for r 1 and r 2, we can find the at the equator r 1 equal to b square by a and r 2 equal to a. So, therefore, n phi becomes p a by 2 and n theta becomes p a into 1 minus s square by 2 b square. So, from this expression, it is clear that n phi is always positive, that means, n phi is always tensile in nature. However, n theta can reverse its nature. So, n theta is p a into 1 minus s square by 2 b square. P and a are quantity which are positive, but this quantity may be positive or may be negative depending on this a by b ratio. Now, it can be seen that n theta becomes negative if 1 minus a square by 2 b square is less than 0. Now, this is possible when a by b is greater than root 2, that is 1.414. So, it becomes negative at the equator if a by b is greater than root 2, that is 1.414. So, that means your this n theta changes sign, that is illustrated with an example. Say we take the ratio of semi major axis to semi minor axis as 1. So, that is the case of a sphere, and we know that in case of sphere this the stresses are same and it is P a by 2. If a is the radius of the sphere, here it is denoted as semi major axis. So, the stresses are P a by 2, that is 0.5 P a. Now, here you can see for a by b ratio n phi n theta is constant magnitude and it is always tensile. Okay. Now, when a by b is greater than 1.414, that I have told, it will change the nature of the forces from tension to compression. Now, here the plot is shown with a by b equal to 2, that is the ratio of semi major axis to the semi minor axis is greater than 1.414, that is root 2. N phi is P r 2 by 2. So, r 2 if you put here, r 2 is a positive quantity. So, if you put here, you will get always the positive forces here, but it will vary according to the level of the point, that is at which meridional angle it is located. So, depending on the value of phi, it will vary, but you will see that n theta changes sign. So, n theta for some value it will be some value of n phi, it will be positive, and then it will cross the axis and it will go to the compression region. So, when compressive forces are developed in the shell, especially in the elliptical vessel, which is used as a head closure. So, in the knuckle region, the compressive stresses are harmful actually. Compressive stresses in a metallic pressure vessel and in the form of a closure head may cause some buckling. So, this is given as an evidence from some research paper, and which is carried out experimentally to test the behavior of the closure head under the action of internal pressure, and a model test is carried out, and I will show a picture of this the knuckle region of the ellipsoidal shell, where the buckling is taking place due to compressive stresses developed. Compressive stresses is developed in the circumferential direction when a by b ratio is greater than root 2. So, this test results or test picture is taken from a book that is written by Fire and Harvey on high pressure vessels. So, initial buckling is observed here in this knuckle region of the head closure. Okay. So, today I have discussed the pressure vessels of types, that is circular cylindrical type, circular conical type, and spherical vessel, and vessels in the form of ellipsoidal of revolution. So, next day I will start these vessels in the form of torus. Okay. Thank you very much.